Hello, today we will discuss about the shear force and the bending moment acting across the length of a beam. You all are very familiar with the structural member beam, which is a member that carries the moments, or it is the one which is designed to carry the moments. And the beams are generally carries different types of load, point loads, uniformly distributed load, uniformly varying load, and different types of loads are there. So this beam carries the loads, and also it resists the moment or the bending effect created by the loads. So we are interested to know what is the value of this particular loads acting at different locations of the beam, and also what is the value of bending moment across the length of the beam, and we have to plot the distribution. So this here in this under this topic we have to do certain calculation analytically, and we have to convert this calculations to a sketch to get the distribution. So let us move ahead and see what or how we can do this. It's a really interesting topic, so keep attention to all the points that we are going to discuss, because if you miss a single point you will find it very difficult to do the analytical calculations as well as the drawing. So every point is interconnected, so make sure that you don't lose your concentration. So moving ahead, we all are very familiar with the types of beam. Here you have the first three sets of beams are the statically determinate beams, which can be solved using the conventional equilibrium equations. This is the one which we have discussed early in your first module, or the statically determinate members. Same laws are applicable here also, and the last three are statically indeterminate. So if you look here, we have a simply supported beam, an overhanging beam, and a cantilever beam. So I think there is no need to explain much about these type of beams because they are self-explanatory. But one thing I will explain here about the reactions, how to supply the reactions. The answer is very simple. See, if you arrest something in the sense means if you arrest the motion in one direction, definitely you have to compensate with a reaction. So if you look at the section A, here you have arrested both the x as well as the y motion, so you have to supply with two reactions. But if you consider the point here B, the y motion is arrested, so definitely you have to supply or compensate with the y reaction. So that is how you supply the reactions into the system, or when you draw the free body diagram, you have to give the reactions, or you have to give loads instead of the supports. That's what's the meaning of free body diagram. So these supports are replaced by the reactions, and we have different types of supports here. So that's a general topic. So kindly, if you have some doubt regarding this topic, you kindly refer some standard textbooks and see the different types of beams as well as different types of loads. Now let us move forward and we'll discuss about the shear force. What exactly is the meaning of shear force? See, if you take a beam like this, we can see that 2 point dots P1 and P2 are acting at two different points, and you have a UDL load, so some particular Newton per meter. It can be kilonewton per meter also. And if you look at different section, say this is a section 1, you have a section CC here, let us take a section 2 here, 2. So if you look at these three sections, the amount of vertical load acting at these sections are different. Why? Because of the variation in the load, because of the variation in the location of the load. So it can be same, but usually one thing we can conclude is that the value at these three locations are different. Not only in these three locations, from point B to point A, if you travel, the value of this vertical load is going to be different. So we are interested to plot the variation of this vertical load. So in order to draw the variation of this vertical load, we have to follow a sign convention. So that is the tricky part, because we are adopting this particular sign convention for the sake of simplicity. Okay. Before you go to the analysis of the shear force, two fundamental things you have to keep in your mind. The first thing is that all the systems that we discuss here is in static equilibrium. There is no dynamic condition here, because that means body is completely in rest. If you take the section 1, if you take the section CC, if you take the section 2, all the sections are in static equilibrium. The net force is 0. The net moment is 0. But it doesn't mean that the load acting at that particular section is 0. The net value is 0, but if you take sections, section by section, the load is going to be different. Totality is 0. That is the first thing you have to keep in your mind. So definitely, based upon the section that we are going to consider, the value of the shear force as well as the bending moment is going to change. Second thing is that always you have to consider a section which is traveling right ahead of us. Suppose if you travel from your right hand side to the left hand side, this is the usual way I practice. So if you travel from the right hand side to left hand side, you have to consider a section, an imaginary section, say CC, which is traveling right ahead of us. And based upon this section, we are going to give the or assign the sign for the different loads. And that's what given here. You consider the section XX, and if you look towards the right hand side, and if you find a load which is acting in the downward direction, this is considered as positive. Okay, so it's very simple. You take a beam, and if you take a section, you are starting from the right hand side and you are traveling towards the left hand side. So as you travel, this particular section is going to travel right ahead of you. And if you find a load which is acting on your right hand side towards the downward direction, it is positive, then the one which is in the upward direction is negative. If you apply this particular law here at the section CC, we can say that P2 will be taking the sign positive, and the reaction at B is going to take the value negative. Why? Because P2 is the force which is acting on the right hand side in the downward direction, and that is considered as positive. And R2, the horizontal reaction RB, or the vertical reaction, not the horizontal reaction, the vertical reaction RB is acting on the right hand side in the upward direction, which is a negative quantity. So here we are not using the upward positive, downward positive. No, don't generalize like that. Always this particular sign convention is based upon this sectional plane. Or in simple words, I will say like this: if you consider a section here, a force acting in the upward direction is negative, the one is acting here is downward direction is positive. So if you look at the left hand side, this is going to be positive and this is going to be negative. You might be having some confusion here. Don't worry, when we solve 2-3 questions, this part will be okay. So but just keep this sign convention in your mind. Don't forget this. So because we have to mix certain sign conventions here, so you find it difficult to follow the sign conventions. So this is how you should remember the sign convention for now. Now we'll go forward to look into the sign convention used for the bending moments. See, for the bending moment, what we have to do is same section we have to consider. So if you look here, we have a section XX here, and we have a load W here, which is acting at a length L from the fixed support. See, as the length changes from X to L, the value of moment is going to be different, because the value of moment is nothing but W into X. So the value of moment at the location B is going to be 0. As the length increases from 0 to, that means X is equal to 0 to here X is equal to L, the moment is going to vary. So what we are going to do is plot this variation across the length. Here also you have to consider a sign or give a sign for the moment. So when you give the sign for a moment, the conventional methodology should not be adopted here. That means we usual way of practice is that we use that clockwise is considered as positive and counterclockwise moment is considered as negative. So the opposite also right. That is a usual way of representing the signs of the or conventional that we have used to give the sign for the bending moments. But this is not the one that we are going to use here. We are going to use a completely different methodology. That methodology is the effect. It's purely based upon the effect. We have to take individual loads. That's very important. When you consider the shear force as well as the bending moment, you have to take one force at a time. You consider one force at a time, you take the effect of that particular force or give the corresponding sign for that particular force, then you analyze it. Once you analyze the particular force, you leave it. Don't worry about that particular force because we have already taken the effect of that particular load. Now there is no need to worry about that particular load, so we can consider that it is being eliminated from the system. Okay, so if you apply that particular approach here, see what is going to be the effect created by the load W at the section X, or how the beam is going to bend. The beam is going to bend like this, right? The beam is going to bend like this. The bending is something like this. Such kind of bendings are called as fogging, and that is negative. So if we are using this kind of analysis or the sign convention methodology, then we can say that this kind of bendings are called as fogging type and they are given negative sign. This type of, the first one is a sagging type. This is a positive one. So this is a positive one and this is a negative one. Now I will show you 2-3 cases. If you take the second one, if you take the second member beam, we have two loads here. Let's say this is P1, this is and P2. So if I take this particular section, say this, anyway, I have to travel from here to the right hand side to the left hand side. For the explanation, right, I'm taking a section in between P1 and P2. You can take a section between A and P1 also, no issue. So if you consider a section like this, you have got two loads here. One is the vertical reaction at B and second one is the load at P2. See, if you take the moment due to the reaction RB, this load is going to create a bending like this, or effect like this. It will not create, but it has a tendency to create a bending like this. So this comes under the sagging type. Therefore, the moment created by this reaction, say L1, so the value of RB into L1 will be given a positive sign. And if you take P2, we have considered RB and we have taken the effect, just nothing but RB into L. And the nature is sagging, so a positive sign is given. We have eliminated the RB. Now we have to consider P2. So what is the effect created by what is the magnitude created by P2? Let us say this is going to be L2. So the moment created by P2 is nothing but P2 into L2. Now we have to give a sign for this. So how will we give P2 into L2? How this P2 is going to bend the beam? So it is going to bend the beam like this. So this is a fogging type. So this is a negative. That means negative P2 into L2. That means if you take the moment about the X, the net moment is positive RB into L1, negative minus P2 into L2. Here we have not used the clockwise and anti-clockwise sign convention. Okay, so for the second case, I told that P2 is going to create a fogging type of moment. So some of you might be confusing, sir, how this particular beam can bend like this when you have a support like this? I think I have already explained the answer for that, because see, I have replaced the support by a force RB in the free body diagram, and I told you that once we calculate or analyze this RB, we have to consider that this RB is absent in the system. So when I took the effect of RB as RB into L, I have eliminated this force. Now RB is not there in the system. Now we will take the P2 and analyze it separately. So this methodology should be followed. Consider every force individually. Don't worry about the totality. If you consider a system as a total, if you consider the total system, you will end up in confusion. We are not considering the net effect. We are considering the individual effect. That is the correct way of analyzing it. So you consider the individual effects, then only you can give the sign. Okay. So this is the sign convention we use for the bending. Now we have to derive the relationship between the shear force, bending, as well as the loading. So right now we have a load W here. We will consider a small area dx here. So if you take the dx here, we have a vertical force here here. So when you move from section C to C dash, definitely the moment as well as the shear force is going to change. That I have already told you. So if you consider the point C, we have a vertical load V here and moment M here. And if you consider section C, there will be a variation for the shear force, that is represented by V plus delta V. And obviously there will be a variation in the moment also. So the initial assumption that, not the assumption, the initial fact that we have discussed has satisfied here. That means the value of shear force is going to change from section to section. Similar the case of moment. Now we will discuss about the equilibrium here. So let us say, let us write the net force in the y direction at C equal to 0. Here also you have to do the same sign convention. I am going to take the section here at CC. This is the section I have. So if you look at this section, we have one force V here, V plus delta V here. So let us, and also the external loading here. So how will we write? So W into delta X, that is going to be total load, that is going to be positive because it is acting on the right hand side in the downward direction. So we can say that W into delta X is positive. So we have another one, V plus delta V, that is also positive. Right? We have another force V here, it is a negative force V. So apart from these four forces, 1, 2, 3 and 4, we don't have any other vertical loads. So if we equate this to 0, these two V will get cancelled out. So we can say that delta V divided by delta X is equal to minus W. Or in other words, we can say that delta dV by dx is going to be minus W. This means that the slope of the shear force will give the negative of the loading. This is the relationship between the shear force and the loading. If we consider the moment happening at the section C, same similar kind of relations can be obtained. So let us take the moment about the C and equate it to 0. So we have an M here, right? Minus we have an M plus delta M here. Now we have to consider the moment of V plus delta V as well as the UDL. So if we take the moment about V plus delta V, we can say that V plus delta V into what? The distance delta X is going to fetch you the moment caused by the V plus delta V. And now the last moment that we have to consider is contributed by the UDL W. So the net load is going to be W into delta X, and the distance is going to be delta X by 2. That is given here, delta X by 2. That means if you convert the UDL into a point load, the net load W into L will be acting at the midspan of the UDL. So the midspan of this UDL is delta X by 2. So this has to be equal to 0. If you expand this we can say that m minus delta m plus v into delta x plus delta v into delta x plus w into delta x square by 2 equal to 0. So m and m will get cancelled out. Delta v into delta x, both are very small quantities, so the multiplication, the product will also be very small value, so we will neglect this. Similar the case of the last term, w into delta x is very small. If you square it again, it is going to be small, so this is also equal to 0. So what is left with is delta m plus v into delta x is equal to 0. We can say that v is equal to delta m by delta x, or in other words dm by dx. So we can conclude that the rate of change of bending moment will give you the value of shear force, and the rate of change of shear force will give you the negative of the loading. So in a way, this can be called as a slope. This is also a slope. So the slope of the shear force diagram will fetch you the load applied, and the slope of the bending moment will fetch you the shear force. So this slope concept will help you to understand the variation or the methodology to draw the shear force as well as the bending moments. So let us move forward to see some more interesting facts. So I have told you that dm by dx is the slope of the shear force diagram at each point will give you the distributed load intensity. Similarly, for the case of bending moment diagram. And if you integrate to find the value of delta v, we can say that wx into dx. So this is an alternative way of expressing the system. So if you want to find out the net shear force, you calculate the area under the distributed load. Similarly, if you want to calculate the change in moment, you calculate the area under the shear force diagram. These are two alternative ways of explaining the relationship. So this is a very important relationship we have to keep in our mind. Now let us discuss how this shear force and bending moment are being drawn. For that, we have to use some sketching methods like straight lines, inline straight lines, and that is being explained here. So for a shear force diagram, if you want to connect between 2 point loads, we will be using a horizontal line, and for a UDL we will be using an inclined line, and for a UVL we will be using a 2-degree parabola. Similarly, for the bending moment, we will be using an inclined line for the point load, and the 2-degree parabola will be used for the UDL, and the 3rd-degree parabola will be used for the UVL. So there is one alternative or easy method to remember this particular table. So let us put it like this. So first type of loading is the point load. Then what will be the shear force diagram? It will be a horizontal straight line. Then the bending moment diagram will be an inclined straight line. The second type of loading is the horizontal straight line loading, horizontal straight line load, or called as the UDL, right? The UDLs are represented like this. So this is in a way we can say that's a horizontal type of loading, straight line loading. So if this is a straight line loading, then the shape of the shear force diagram is going to be an inclined straight line, and this is going to be a 2nd-degree parabola. So what is the third type of loading? Inclined straight line loading. Inclined straight line loading, or it is called as UVL, because UVL are generally shown like a triangle, right? So this is an inclined straight line loading. So the shear force is going to be a 2nd-degree parabola, and this is going to be a 3rd-degree parabola. So this is, in this way you can easily interconnect the shape. So you have to keep this particular system in your mind. So this much things should be kept in your mind when you go to the analysis part. So you have to remember about the sections, you have to remember about the sign conventions. You have to remember about the lines that has or lines of the nature of the curve that you have to use for connecting the various points. So once you are thorough with these things, we are going to apply them into the system. And one more thing I want to explain here is about the point of contraflexure and point of inflection. So point of contraflexure is the point where the bending moment changes its sign. Bending moment may not be positive always. It may change from positive to negative. So that particular point where the bending moment changes its sign is called as the point of contraflexure. And the point of inflection is the one where the shear force becomes zero. So these two are some general terminologies that we used in the shear force as well as the bending moment diagram. So what all things should be kept in your mind before you start drawing a shear force diagram as well as the bending moment diagram? See, this shear force diagram shows the variation of shear force along the length of the beam. That is the first thing that you have to understand. That means you have to find the shear force at every section. Now the question is, which all points we have to consider? So answer is, you have to consider every location where there is an abrupt change in the loading. So when you start to travel from point 1 to point 2, wherever there is an abrupt change in the loading, you have to consider that particular point for calculation. Because if you take a section from left to right, we can have infinite section. So that's not possible. So we'll be limiting our section to some particular areas. And that particular area is the one where there is an abrupt change in the loading is not. And sign convention should be based upon the individual lots. We have to consider individual lots based on the section, and we have to give the sign. And you consider only one side of a section at a time. So when you analyze a beam, don't look into your right hand side as well as your left hand side at a time. So if you add the right hand side as well as left hand side, net value is going to be 0 because of the equilibrium condition. So you consider only one side to analyze. So another important point you have to keep in your mind is about the variation in the shear force diagram. That means there can be a step-like variation like this. Such kind of step-like variations will be noted at the locations of point load. So if you have a beam like this and if you have a point load here, the shear force diagram will have a step-like variation like this. That's a very important point to be kept in your mind. So similar kind of precautionary measures should be taken before you start with the bending moment diagram. So what is that? It gives the variation of bending moment across the length of the beam, and you have to take the moment about all the points where there is a significant change in loading. That is also another important. Or in other words, I can say that you have to take the moment about all the points, or you have to consider all the points that we have taken for the shear force. And sometimes we may need to go for more points also. That I will explain while solving a problem. And you have to use the same methodology of section that we have adopted for the drawing of shear force diagram. And consider the effect of load individually and assign the sign corresponding to that. So there will be a sudden change in the bending moment diagram where a concentrated moment. Suppose if you have a beam and if you have a moment like this, some m Newton meter. So in the bending moment diagram, there can be a variation like this, a step-like variation, something like this. Variation will be there. So this much point has to be kept in your mind. Along with these points, the most important point you have to keep or remember here is about the last one, that apart from the points that we have considered for the shear force diagram, we have to consider points where the shear force becomes 0, because wherever there is a location where you have a shear force equal to 0, there you can expect to have a maximum value of bending moment. So additional points has to be considered by looking into the value of shear force. So this much point should be kept in your mind before you start drawing the shear force diagram as well as the bending moment diagram. So you kindly go through some standard textbooks and try to read things out. So don't worry about the diagrams. Diagrams will be can be understood by just practicing it. So right now you just follow the sign conventions and the methodology that I have told you. And once we start to apply these things like the sign convention, the nature of the graph, everything into the system, you will slowly pick up. So it will take some time. So first you go through this lecture again and again, and you will note down all the significant points. And to have a better understanding of the shear force and bending moment diagram, I can suggest you one thing. See, you write down all these sign conventions. For example, you write down this particular table in a paper. Along with that, you write down the relationship between this. Along that, you write down the sign convention that you have to use in a sheet of paper. And you use this particular sheet of paper as a reference material while you solving the problem. So after 5 or 6 questions, there is no need to use this paper further because you will be expert in this. So that is an easiest way to tackle this kind of problems. So kindly go through this lecture 2-3 times, note down all the important points. So thank you. We'll meet with the tutorial part in the coming video.